quiz number 3. Only 10 questions today. The first one, the bubble sort, basic operations. Comparison, not the swap. Be careful. Okay? Although we do these two operations, remember, for the swap, sometimes, many times, we do not do swap. All right? Yeah? If we do not find an inversion, we do not do swap. Okay? Only we detect, we find an inversion, we do swap. Yeah. But we always do comparisons. That reason, comparison is the basic operation. Yeah. That's simple. The second one, adjacent. So this one, do not answer this question only based on the logic. Because when I grade similar questions on the paper assignment, several students, they probably they didn't follow the class closely. They just use the basic logic. But even use the logic, why it's not correct? Yeah, because based on the logic, given array not contain an adjacent inversion, a special type of inversion. So then all the elements must be in place. That does not contain any adjacent. Yeah. True. In place. No adjacent inversion. Because if no adjacent inversion, that means no global inversion. No inversion. No inversion. The transitivity problem. Remember, transitivity problem can make the equivalence statement. If you use an adjacent inversion, global inversion, these two statements are equivalent. Why? Because of the transitivity problem. Okay? Right. Number 3, minimum number of inversion. Unordered, I hope, when you read the question, you do not miss any important word, unordered. So it cannot be 0, right? If it's 0, order. So the minimum number is 1, right? Yeah. Non-zero, the minimum number is 1. After that, you need to make sure 1 is possible. The inversion 1 is possible. Can you make a simple example that 1 is possible? Sometimes construct a simple example is important. Like a question like this. Construct simple example. Important. So here we need to find a simple array with only 1 inversion. How about 2, 1, after, it's an inversion. After that, ascending order. 3, 4, 3, 4, 5. Okay? Yeah. So you can see only 1 inversion. If you swap the first 2 elements, you get an ascending order array. Yeah. Only 1. So making some special example. Later we have a few harder questions. Usually, many students feel hard to construct examples like this. Okay? Yeah. This one, how to count all the inversions. Do not miss anyone. Here I show you how to count all the inversions. You need to follow some order. Okay, yeah. Total number of inversions. Let's count. First round, second round. Okay. first one, we fix the first element, 5. Okay? 5 for the first inversion. 5, 2, second inversion. 5, 1, third inversion. 5, 3, 4 inversions. Starting with the first element, we have 4 inversions. All right. Second, we want to start with second element, 4, but do not go back. Okay? Do not go back to use element 5. No, we already passed that. Okay? 4, 2, 1, 4, 1, 4, 3. Okay? All right. Then start with 2, 2, 1, but not 2, 3. So the next one, 1, 3 is not inverted. So nothing, nothing. Okay. 8, right? Total number 8. How about that? This way. Okay. Follow this order. Okay. Answer 8. Do not miss anyone, but do not count any inversion more than once. These 2 things. All right. Number 5, an efficient algorithm does not have to perform well. True. Why? Let me explain. For relatively small problem size. Okay? Yeah. So we'll compare 2 algorithms for their efficiencies. Which one better? Look at n relatively large. Do not look at relatively small problem. Why? Remember, when we draw figures for asymptotic notations, one below another one, remember we have a vertical line, n0. We do not look at the part before that n0, right? Why we ignore that part? That means for the size, relatively small, not important. So we ignore that part. Okay? Size, relatively small, not important. Not important, that means faster algorithm could be slower in this part. Slower algorithm could be faster in this part. Okay? Yeah. So, a lot of distortion. So we should not look at this part. Why? Let me explain why. Let me ask you why. The reason. Let me explain. Reason. Overhead. Overhead. What's that? In order to run your algorithm, you need to do a lot of preparation, right? You need to prepare your data. You need to do a lot of preparation things. So that part, that's the overhead part. When you do preparation, it takes time. It takes time. Okay? Probably for faster algorithm, you need to do more preparation. Right? So it will be slower, this part, overhead part. But the overhead part, remember after preparation, when we increase the problem size, we do not grow the overhead part. Okay? Yeah, we do not grow this overhead part. Pretty much fixed. The overhead part, pretty much fixed. Okay? So when the problem size is very large, this overhead part becomes very, very small. Okay? Yeah. Percentage-wise, very, very small. So we can ignore. Yeah, we can ignore. Yeah. So that's the reason. So for this question, we understand efficiency this way. So that's an important point. Algorithm efficiency understanding. Okay, yeah. All right. If we can solve a computing problem with both iterative and recursive, which one uses more resources? Recursive. Remember that stack. I remember how to implement recursive algorithm in computer main memory. We use the stack data structure, right? So we push unknown function calls into the stack, and the stack could be very deep. The deeper the stack is, more resource used. But for iterative method, no stack. We do not use stack. Okay? So iteration. So we always find the intermediate values, then use it for the next one. But we do not use stack. No deep stack used. So less resource. All right. Number 7. When we calculate the greatest common divisor of two positive integers, there are two methods: prime factorization, Euclid. Yeah. So, Euclid. So we avoid very slow prime factorization operation. Very slow, extremely slow. Okay. Yeah. So, all right. Number 8. Yeah, greatest common divisor, but which tool we rely on? Division. Division. We do problem size reduction by the division. That's it. All right. Yeah. Some easy questions, many easy questions, but you need to follow the lecture closely. Number 9. Not valid definition. No valid definition. GCD of 0, 0. Let me explain a little more. Yeah. So in the class, for this question, I just told you GCD of 0, 0 not defined. Here, let me explain a little more. Why not defined? How to see it? A little more information. Because when you consider here n equals 0, and also equal to 0. We want to see greatest common divisor, right? We want to look at the greatest common divisor. All right. So let's look at the divisor, common divisor. Greatest next, right? Let's look at the common divisor. We want to consider, common divisor. Okay. Is 1 common divisor? 0 over 1 equals 0. Integer, right? Second 0 over 1 equals 0, also 0, right? Integer. Yeah. You put 1 at the denominator, you get integer, right? Yeah. And on the numerator, divisor, denominator, you get an integer. So that's like, so 1 is a common divisor, right? How about 2? Is 2 common divisor? 3 common divisor, right? 4 common divisor all the way, and any positive integer and common divisor, and you can go to infinity, right? Which one the greatest. No greatest, all right? No fixed number could be the greatest common divisor because all these positive integers are common divisors of these two numbers. So that's why it is not defined. Nobody can provide a reasonable definition without causing a problem. Not defined. Simple explanation. Now you feel better because the problem here. Last question of here. When we solve the power of not yet, so we need to go back to the procedure. We apply it twice, right? Good. First, apply the first time, we solve the n-1, this problem, then move the bottom disk to the destination pad. Then another n-1 disk problem, back to the destination pad. Only two easy questions. So if you are familiar with our nodes, materials, very easy. Many questions. This one, you can see 4 or 5 questions. Pretty straightforward from our notes. All right, any question?
All right. Which module did you go over the bubble sort?
Bubble sort. Bubble sort question here.
Yeah, I'm just trying to remember where we would have looked at. Trying to remember where we looked at that problem.
Bubble sort. I remember we only talk about the basic operation, right? Do you mean this question or?
Yeah, I was referring to that question. I just wanted to know where in the notes we talked. Like, was it module 3 or module 2?
Right, the notes. Yeah, as I remember, bubble sort, brute force, right?
Okay.
Yeah. When we talk about brute force algorithm, which one? Module 2 part D. Is it module 2 part D approximately? Yeah. Yeah. Bubble sort.
I see it.
Yeah. Yeah. So approximately. Yeah. So some of you, yeah, you can check. Let me know. Based on my impression. Okay. Based on my impression. Yeah. But module 2, we do asymptotic notations. And brute force, right? Yeah. Brute force, string matching problem. If it, yeah, it may not be RD, right? It is? Oh, good. Very good. Yeah. Oh, okay. Yeah. All right. So next, let's finish our last topic. Last topic. Okay. Actually, I do not need to stop because I put it right below. Why? Stop. I can continue. So D13, linear recurrence relation. This part, actually, it is an old topic for you. You should learn this topic in history math. Well, probably a long time ago. I like to, repeat the whole story, but I will add a lot of background, a lot of, useful information. But I believe, because I look at the text textbook in the history math. There is a section about this topic. And you have a standard procedure how to solve it. All right, so, but let me just my remote control. Yesterday, I had this problem. Remote control not working. The way I use this one. Very weak. Try to start over. Just restart it. Yeah. So here we derived. So here our goal. We want to solve this. All right. We want to solve this recurrence relation. First, let's look at its name. It has a long name. But let me explain why we call this long name. Second order linear homogeneous recurrence relation with constant coefficients. Why its name is so long? Second order, not first order. Second order, not first order. Here you can see two terms at the right hand side. Two terms. Two Fibonacci number terms. That's sequence. So we have a sequence, F sequence. Two adjacent terms in that sequence are used at the right hand side. So for the second, that's the second order. Okay? Fn can be represented by two consecutive previous sequence numbers. Second order. Now the first order, let's recall the first order in our power of Hanoi problem. Power of Hanoi problem. What's that? If I write it in a similar way, the recurrence relation is Cn. C, although we use function, if I use this way, Cn equals 2 Cn minus 1 plus 1. Right? You can see this is the first order. Because at the right hand side, only one sequence number, C sequence, that's right. Okay? So we only use one previous sequence number. First order, second order. Linear, homogeneous. Linear, all the terms are linear. Okay? All the terms are linear. Linear, you know linear. Okay? Constant multiple of that sequence number. That's linear. Constant multiple. You cannot put square. If you put square, that's non-linear. Okay? For example, Fn equals F square n minus 1 plus Fn minus 2. Non-linear. Okay? Square term. Non-linear. It will be very difficult because the linear case, that's probably the easiest case to solve. So linear. We like the linear equations. All right, so this is linear. Homogeneous. Another property is homogeneous. That means no constant term. Homogeneous corresponds to no constant term. Okay? Yeah. If you look at our power of Hanoi, this problem, there is a constant term. Hey, 1 plus 1, that's the constant term. If you have a constant term, it is a little harder to solve. So the first step, we want to remove the constant term. Remember, we introduced the D sequence, D function. We plus 1 both sides, so we can define a D function. After that, the constant is gone. After the constant is gone, we get a homogeneous equation, right? Here, when we start, we have a homogeneous equation. That's a good property. Easier, make the question easier. Yeah. So homogeneous recurrence relation with constant coefficients. Constantly, the linear coefficients, 1 and 1. That's constant. Constant coefficient. Right? Yeah. Because what is the non-constant coefficient? Let me show you an example. Non-constant. Fn equals n times Fn minus 1 plus n minus 1 times Fn minus 2. How about that? Non-constant coefficient. That could be very hard. Think about it. Non-constant coefficient. Much harder. So here you can see all the properties we have for this equation make it relatively easy. Second order linear homogeneous recurrence relation with constant coefficients. Next, we solve it. The general form like this. Capital A, capital B. Constant coefficient. Not necessarily 1, could be any constant. But B cannot be 0. Otherwise, it becomes the first order. If B equals 0, we get a first order. Here we want to solve second order, not first order. For Fibonacci, capital A equals capital B equals 1. But the general case, here we want to find a systematic method to solve. Systematic method. All right. Yeah, it's the Fibonacci case. But let us solve the Fibonacci recurrence relation. Well, the method can be generalized to the general case. All right. To start, we want to find some insight. So take a special view. What's that? We consider a sequence here, a sequence. The sequence should satisfy the given recurrence relation. So we want to study this sequence. All right. We guess the structure of the sequence. Guess the structure. This time, not the result, the structure. Structure is important. So to guess the structure, this step, critical. If you guess it right, then the problem becomes very easy. Guess the structure. Can you imagine some reasonable structure for the sequence? It's not easy. Here, we guess the structure should be t to the kth power. This sequence, we can call geometric sequence. Geometric sequence. Okay? Not arithmetic sequence, geometric sequence. But the question is, why you make this guess? Not very intuitive, right? experience solving this first order recurrence relation for the power of 1 point. If you connect that, our d function is what is the d function? Our d n equals 2 to the nth power, right? Our first order linear recurrence relation, the solution is 2 to the nth power. Is it a geometric sequence? When you change n from 1, 2, 3, 4, 5, do you get a geometric sequence 2 to the k? Do you get that geometric sequence? Just t is different. Now t is 2. Here, yeah, because when we connect to that one, we try to extend that idea a little more. Can we try the same structure but with different t, different base number in the sequence, geometric sequence? So t here, we change to the unknown t here, but we adopt the structure. We want to try if it works. In problem solving, sometimes you need to make some very brave guess. Imaginary brave guess. Very brave. Then you have a better chance to find a solution. If you worry too much, do not do it in this way, do not do it in that way, worry too much, then you reduce your chance of success. Here, we make this broad, brave guess. Let's try this sequence, t to the k. With this structure, let's plug in. Let's assume a sub k equals t to the power of k. We assume that. How about that? Okay. Plug in. Yeah. All right. So at this point, don't worry about the initial condition. Yeah. Although we know there is some initial condition, but let's take care of the major part. That minor part we leave. After we solve the major part, then we add a minor part back to it. Question: can we find a solution with this structure? Let's try. Okay. Plug in and see what we can get. Yeah, replace a sub k by t to the k. Then similarly, a sub k minus 1 should be replaced by t to the k minus 1, and so on. Yeah. Plug in. Nothing wrong here. If a sub k equals t to the k, we can do the substitution. Okay? All right. Now this question, can we solve this question? This new question? It's not recurrence, right? It's an ordinary equation. It's not a recurrence relation anymore, right? So after simplification, we cancel out t to the k minus 2 power. Cancel out this term. Do division of this term, both sides. After cancellation, t squared equals t plus 1. Very simple. This equation, do you feel it is quite familiar? This equation, have you seen this before? This equation? Golden ratio, remember, is it golden ratio equation, quadratic equation, that we find the golden ratio, right? All right, so t squared minus t minus 1, okay? We have quadratic formula to find a solution. let's apply the quadratic formula. There are two solutions. Right. T1, 1 plus root 5 over 2. T2, 1 minus root 5 over 2. Two solutions. Remember, when we calculate the golden ratio, we get two possible solutions, but we drop the second one, right? We drop the second one. The golden ratio, we know the meaning of the golden ratio definition. So we drop the second one. Here the question, should we drop the second T2 here, similar to the golden ratio way? Golden ratio, we drop the second one, because second one is negative. Here, the T means certain number. If we plug in here, the recurrence relation should be satisfied. That's the T, right? Not necessarily the golden ratio. Why this T should be the golden ratio? There is no reason this T should be the golden ratio, okay? No reason. What's the requirement for this T? The T, we only need some number if non-zero. It must be non-zero, okay? Yeah. Some non-zero number, if we plug in, we can, this equation is satisfied. That's all we need. If T is negative, no problem, right? Yeah. There is no reason T cannot be a negative. Negative, because this T has nothing to do with the ratio of two line segments. Remember, the golden ratio is the ratio of two line segments. Here, our T, we do not define our T in that way. Our T is just a number, non-zero number. That means our second T solution cannot be dropped. We should keep it. Keep it. No reason to drop it. So we have two solutions. We use both solutions. But we know it's not an integer solution. Definitely it's not an integer solution. Yeah? Not an integer solution. But we know our Fibonacci numbers must be integer solutions. Don't worry. Here, another thing, as I said before, take some brave actions. Yeah, because some people, when you get a non-integer T numbers here, you may feel something could be wrong. We should not move forward because non-integer. We don't like non-integer numbers. No. Okay? Even non-integer numbers move bravely forward. Even non-integer numbers, let's keep pushing. Keep pushing. Let's look at the next step. This time, we have two special solutions for this equation. E1, T2. So if we plug in each solution back to our T sequence, the equation, the original equation, but we use T sequence. Now, let's plug in. The first solution, if we plug in, we get this equality. If we plug in a second solution into that sequence equation, we get the second equality. Both correct, right? Both correct. So we have two special solutions. Two special solutions. Next step is critical. Now we want to move another step forward. It's a critical step moving forward. So what's that? Here, remember, these two are special solutions. Now, we want to use these two special solutions to form a more general solution. Yeah. we use these two special solutions as the building blocks to construct a new solution, new, more general solution. That's what we want to look at. Building blocks. Okay. Then we construct a new, more general solution on top of these two building blocks. Okay. How to construct the technique here. There is a technique, useful technique. Very important. Okay. So what's the useful technique? Remember, our recurrence relation, there is a property, useful, important property we can take advantage of it. So what's the property? Remember the long name, second order, linear, homogeneous recurrence relation with constant coefficients. In this long name, there is one critical word we can use. Linear. Linear. The property is the linear rated property. Linear rated property. How to take advantage of this linear rated property? Yeah. Linear rated property, very useful. Yeah. How do we construct a more general solution using these two special solutions by the linearity property? That's the question. Linearity property. Okay? Yeah. Okay. Yeah. All right. Yeah. So here, the reason we need a more general solution, you can see, because these two special solutions, they do not satisfy the initial condition. Initial condition. Not satisfying initial condition. Okay? If we try to make a new solution that satisfies initial condition, then, because initial condition 0, 1, then we will have the integer solution, right? No. Because when you start with 0 and 1, then do the recurrence relation, you get all integer numbers. So here, our goal becomes, we want to find a solution that satisfies the initial condition. If we can do that, okay, we don't worry about the integer, non-integer, because automatically it becomes the integer solution. Yeah. But to satisfy the initial condition, we need to do some special construction. Okay? Yeah. Special work to mix these two special solutions, to combine these two solutions. How to combine, how to mix a concept related to the linearity property. There is some concept related to the linear rating property. Yeah. All right. Yeah. So that's what we want to do. So let's continue. Okay. The technique. We need some special technique to help us construct a new solution that has a chance to satisfy the initial condition. Okay? Yeah. All right. Now, the concept, new concept. Some of you probably heard of it. Okay? So what's the concept? It's called a linear combination of two variables. Have you heard of this concept? Linear combination concept? That's the way we take advantage of the linear rating property. How do we apply the linear rating property? Linear combination. What's the linear combination of two variables, x and y? Okay. This structure. Capital AX plus BY. A constant, B constant, AX plus BY, we call a linear combination of x and y. Here, x refers to our first special solution. Y refers to our second special solution. So we consider a new solution with the form ax plus by. That's the way we take advantage of the linear rate. Because after we take this linear combination form, we get a new solution. We get a new solution. Okay? Yeah. Can you see that? Any linear combination of two solutions is also a solution. Can you see this? This observation is critical. You need to see this observation, this property. Okay? Any linear combination of two solutions is also a solution. Why? Because our recurrence equation is a linear recurrence equation. So let's see why it is correct. Okay. All right, let's take the new form for our solution. Then you plug in, can you get the recurrence relation satisfied? Can you? Yeah. If I go back, let me just go back. Oh, not necessarily go back. Yeah, not necessarily go back. Yeah, why? Because we have here, right? We have two special solutions here. Okay, let me show you why linear combination this way is also a solution. This identity, no problem for you, right? To understand. The second identity, no problem for you, right? Both correct. Right. How about first identity, we multiply A both sides. Also correct, right? The second identity, how about we multiply B both sides? Also correct, right? Two identities. Then we add up these two identities. There should also be a new identity, right? If you add up these two identities, do you get a new solution of this form? Yep. So you can see, using the linear combination structure, we can construct a new solution. Because our recurrence equation is a linear. Linear, we can have this problem. If it's non-linear, you don't have this problem. If you have a square term, you mess up. Okay? If you have a square term, one square, the structure completely messed up. You cannot do this. Fortunately, here we have the linear structure. It works perfect. Works perfect. Okay? Yeah. All right. Let's continue. After that, for arbitrary A, arbitrary B, right? Yeah. The constant. Any capital A value, any capital B value, it's a new solution. So we have freedom to choose capital A, capital B. We have freedom to choose. When we have freedom, can we find a special A, special B to satisfy the initial condition? Yes. That's the purpose. To use these two parameters, A parameter, B parameter. So we can determine an appropriate solution satisfying the given initial condition. All right, let's do the last round work. The final round, we will get the final solution. All right, plug in. Yeah. How to determine capital A, capital B? We have two initial values. Let's plug in n equals 0 and n equals 1. We should get two equations. When n equals 0, let's plug into this formula. And after simplification, capital A plus capital B should be A0. That's 0. So B equals negative A. Let's plug in A equals 1. Yeah, after simplification, yeah, because we can replace B by minus A. Yeah. After simplification, A times root 5 equals 1. So A equals 1 over root 5. Then B equals 1 over negative 1 over root 5. Then let's put it back. Capital A, capital B, back to the original, our new form. Okay? Yeah. Yeah. But we use the golden ratio notation here. 1 minus root I over 2, that is negative 1 over p. So you can see after that substitution, our final solution becomes this one. This is the phi constant. We derive it. We use some systematic method to derive it. Okay? This method can be used solving all second-order linear homogeneous recurrence relation with constant coefficients. All. Okay? And this way, you do not guess, because nobody can guess this one. You calculate it, but try to follow the story. Remember, last time one student asked me, how to do the right way of learning to get good results. Here, I want to tell you, you need to follow the lectures closely. So it's good for you, so you sit in the class. You need to follow the whole story from beginning to end, and do the thinking, okay? So when I talk about, when I do the logical reasoning, you need to follow my thinking, okay? Understand the story, follow the logic, okay? Do not miss this part. If you miss this part, because some students not sitting in the class, after the class, if you want to pick it up, you need much more time, 2 or 3 more times. Because it's very hard to sit down, watch the video from beginning to end, and especially the hard part is following the story. You may get distraction, right? When you sit at home to watch this 1-hour video, you may get a lot of distractions. You couldn't follow the story completely. So if you miss, for example, linear combination part, I may give you linear combination questions. You get lost. What's the linear combination? You get lost, right? Things like that. So the most efficient way of learning, sit here, following the story from beginning to end. That's the best scenario. Best scenario. Other than that, after the class, you want to recover, you need twice as many, even more time to get similar understanding. So that's the point. That's the point. Okay, all right. Yeah, so I finished this last part. I have a few minutes. Do you have any special questions you want to ask me related to the homework assignment? Probably I can only answer 1 at the most 2 questions. Try to find relatively hard questions. Here, if you don't ask me, I will guess. All right, I will guess.
Oh, how much explaining are we supposed to do in our answer?
How much explanation?
Yeah.
All right, that's only related to the last 2 questions, right? Yeah.
Any, I mean, for
What?
both of them, you just want.
Yeah.
me to
Oh,
say
yeah.
anything?
Important thing, I need to let you know. Yeah, answering your question. When you see solutions, you need to provide more details. When you see answer, you do not have to. Okay? Yeah. All right, that's the first thing. Second thing, all right. Full solution, write the main steps. Okay? Let me understand. You really solve it. Okay? Just enough information to convince me you solve it. All right? Yeah. All right. But for these questions, you see, answer, although you do not have to provide the details, not necessary, just the answer. But to your benefit, if you can put some important information, some important formula or main steps, you can earn partial credit. Even if you miss the answer, right? You may calculate the answer wrong. Last step, you got it wrong. But your formula is correct. Your idea is correct. Okay? You show me the important step. Oh, do this way. No. It's correct, but unfortunately, your calculation is wrong. I only take 1 point off if calculation is wrong. But everything else is correct. So you have chance to earn partial credit by providing just a few important steps. If not important, you do not have to. Okay? Important key steps. For example, this Tower of Hanoi, one formula, 2 to the n minus 1. That formula, if you put there, that's helpful, right? Because you know that formula, you can earn partial credit. Okay? Something like that. Right? Yeah. So try to maximize your partial credit. You can probably earn a lot. Even if not perfect, you can earn a lot partial credit. Okay? Yeah. Think about that. All right. Yeah. Last question. If the time we have. For me, yeah, if you don't ask, I don't want to waste time. For me, number 25, right? So I put the last one relatively hard. Okay, all right. Three elements in ascending order already. Yeah. Do not ignore the condition. B, 4 elements in ascending order, right? Yeah. That information you should use. All right. Then we also know after the first comparison, A2 and B2, A2 less than B2. Our goal is we want to find the median of these 7 elements. Median of these 7 elements. Okay? You know what is the median. After the 7 elements are sorted, the one in the middle, that's the median. Okay? We want to find that. Definitely one comparison, we cannot find the median by one comparison. But after one comparison, we can eliminate a few elements. Those elements cannot be the median. We can eliminate them. The question I want to ask you, what are those? Try to maximize. Try to find as many those elements as possible that can be eliminated by the first comparison. All right, that's the first thing. Second thing, when you do the elimination, do the elimination from both sides. Both sides. What's from both sides? Yeah, let me explain. The median, the one right in the middle, we can interpret it as the 4th smallest element, right? The 4th smallest element. If you count from the left side, 4th smallest element. If you count from the right-hand side, the 4th largest element. So you can look at from both sides, largest, smallest, both 4th. 4th smallest, 4th largest, because this increases your chance to do the elimination. Yeah. For example, this median should be the 4th largest element. But you find one element is less than 5 elements. Can you eliminate it? One element, you know, it based on the given information, it is less than 5 elements, then it cannot be the fourth largest, right? Already less than 5 elements. So you can safely eliminate it. All right? Similarly, you find one element is greater than 5 elements. Okay? Greater than 5 elements. You can safely eliminate it, right? Yeah. From 2 sides. Okay? 2 sides to increase the chance for your elimination. That's it. That's already too small. My moon, I forgot to enlarge.
Ja,
Too small.
das ist okay. Du kannst weiter.
You know how it goes.
Yeah.